here that are available on the GitHub release page for LAS 9, the beta software. I did this on Dunkel. It's all set up, ready to go. And when it loads up out of the box, you get LAS configured with some of the default ferret data sets. And so you can start using it right now, checking it out, see how it's going. So we'll do a little bit of that, and then I'll show you how to add your own data to it. So you start out, you make an XY plot of one of the variables in there. You want to check how some of the processes that go on behind the scenes to provide analysis operations. That's probably a good idea to make sure that's all configured correctly. So if I do a time average of this particular variable over this domain, I'll look at the selections. I'm going to have a start of January, end of December as a climatology, so I'm going to compute that average. So I do that process behind the scenes. LAS creates a virtual data set that represents that average, and then it creates a plot of it. So this is the URL of the virtual data set that was created. We can check that out. It's just a regular OpenDAP data set. So if you're used to looking at OpenDAP data, so built into LAS under the LAS context is its own thread server, and under that thread server it automatically creates these virtual data sets. And if you go down here and look at this last variable, it created a variable called ART transformed, which represents that that average. So you can see everything's set up, everything's working. So how can we get our own data into this and start working with it? So this version of LAS includes an admin interface. So when I set it up with an admin password. The admin password is fighting chance. 2 words smashed together, all lowercase. So I'm going to leave this up. If you want to play with it, you can go to the admin interface. You can start messing around with it. I don't care. It's completely disposable installation, just set up for us to goof around with. So there it is, and you have a bunch of tabs that you can interact with the data in your LAS. And so we're going to start out. We're just going to get rid of the default data sets. Those are not particularly interesting to me. So get rid of those. I'm going to change the name of the site from example to PMEL data. I'm going to save that. You're going to notice a bug here that it doesn't actually put up that little bar across the top to let you know that it was working, but I know it worked. So if we see now that the name of the site is now PMEL data. So let's go find some PMEL data that's interesting. I know that we have a bunch of data available. One of the ways that we serve public data is through ERDAP. So here's a ERDAP server that's got engineering data in it. Got a bunch of TableDAP data sets. So if I take this TableDAP URL, copy that, and come over here to this administrative interface, I see down here at the bottom that there is a way to enter all of the TableDAP data sets that are available from a particular ERDAP server. So that's pretty interesting, so I'll just do that. So I'm going to add all those, whatever it was, 30 data sets into LAS. And they're going under the top level PMEL data. So these data are added. They're in the LAS. If you go to the LAS and you reload the page, you're going to see that instead of the default data sets, you have the engineering data sets. They're organized by geometry type by default. That's okay, but it's not really all that interesting to me. All these Dart sites are all mashed together, and the Prowler site's off by itself. So I'm going to reorganize these data to something a little bit more interesting. So the first thing I'm going to do is I'm going to add a container called engineering data, because we're going to add a bunch of different types of PML data in here. So at the top level, we want to be able to have, what did I do? There it is. So I've got engineering data, and then under engineering data, I'm going to add some sites. So I'm going to add the N03. You know, maybe if you were smart, you'd make more informative titles, but for the time being, so you don't have to watch me type, I'm just going to give them these short names. So now under engineering, I have these containers, and so I can go back to my original data, which is here, and over here I can go to this N03 container and I can find data sets that look like they belong there and move those in. So I admit that this is a bit tedious, but it's a lot less tedious than editing XML files. So really quickly we can organize these different types of engineering data by site instead of having them all mashed together by geometry type. All right, so one more. W20 data. So these are all the sites off the coast of Chile. We're going to pretend like those are the ones that are interesting, and the others we're going to decide maybe that they're not interesting. So if we're going to go here, so here's the original collection of data, the discrete geometry data. We'll just delete that, and now we have a set of engineering data, and it's organized. Instead of by geometry, now it's organized by site. So we go back to the LAS, we load that up, and we can start using these data. So here's the engineering data. If we go to the N03 site, look at the 15-minute data, and look at the primary bottom pressure. So we should be getting a plot of the entire history. Fascinating. There's a huge outlier here that sort of makes the graph not very interesting, but we're interested in what happened right here at the end, so we can just highlight that section. So this actually caused us to zoom in time. That's very interesting, but we're going to zoom in time a little bit more. And so now we're looking at just a few weeks of data. That's interesting, but there's the only interactivity we get with this type of plot is the ability to zoom in. So one of the features of LAS9 is we've added some native Google Charts chart type, so you can get a blob of data from ERDAP as a Google Charts data table, can bring it right in. So then now you have that same chart, except it's interactive. You can interrogate the data with your mouse pointer. You can zoom in, scroll along, find the things that are interesting. So there you go, engineering data organized by time series. Now, well, that's kind of cool, but we eliminated a bunch of that data. And one of the things that we eliminated was this Prowler data set, which is actually a profile data set. So let's take a look at that. So there's the data page for that. I'm going to copy that URL and go back to this administrative console. And here under engineering data, I'm going to add this Prowler data. And in this case, it's a single DSG data set. So that URL goes in that spot. And now in my LAS, a profile plot. So this is time on the bottom axis, depth, and so each one of these represents one of the traversals of the device down the cable or up the cable, I'm not sure which, and then the data values at the various depths. So again, you can interact with this plot if you think that this section here is interesting. We're going to do some constraining. Now, one of the interesting things that happens here is that we're going to constrain in 2 dimensions. So we've constrained in depth and we've constrained in date. So we're going to zoom in both in time and in depth against that little block. So that original plot took quite a while to produce. If we go back there and look at that, that was 293,000 points. And when we zoom in, we were able to make that plot much quicker because we had factor of 10 fewer points. So another interesting thing that you might have noticed there is that I used the forward and back buttons in the browser, and the forward and back buttons are active and they show each plot state. So they take you from basically every time you hit that update button, go to the server and get a new plot, that records the state of the system in the forward and back buttons of the browser. So those are available to you. So now we've been using 2 different kinds of discrete geometry data. Of course, LAS has its history in gridded data, and so let's go get some gridded data. So I have running on an internal server some data from the ACLIME project, Alaska Climate Integrated Modeling Project from AL. And so I'm going to add these data into my LAS. So I'm going to go up to the top and I'm going to add a container here called ACLIME. And then underneath there, I'm going to add these 2 data sets separately. So this is an ERDAP server that's serving gridded data, and this is a single NetCDF data source, even though it represents about 4,000 weeks worth of data, represents a couple dozen variables. It's one OpenDAP URL. And so LAS is going to sort all that out by just adding that data set. So we've done that. There's another data set similar where these are the same, from the same model, but these are variables that don't have a depth component, so they're the surface variables. So I happen to know that the URL for that is just the same thing, except we just change this word depth surface. So I'm going to add those in. So now I have another couple of data sets in my LAS. So I go back, I reload that interface, and I'm going to see these new data that are available. Now it's starting to get a little bit more interesting here because we've got 16, 17, 18 data sets, and they're organized here, or they're broken out here by geometry type, profile, time series, grid. But then, as we get more and more data, it becomes more and more interesting to look for data through these search interfaces. So I'm going to look for flux variables. So it turns out that there's a bunch of surface flux variables in this A-climb model output. So I look at net latent heat flux. So by selecting that variable, I get the obvious thing, which is an XY contour plot of that particular variable. So, I mean, that's interesting, but I happen to have noticed that there's a whole bunch of flux variables. They all have the same units. So if I wanted to do a time series, since this is a huge model run, and maybe I want to look at all of these flux variables that have watts per meter squared. They don't have to have the same units, but it just so happens that I know that these do. So I'm looking at a spot of the geometry. I'm not going to look at all 94 years, 100 years. So let's look at a few years of flux data. So let's start 2021, where we're actually, model is doing some predictions and some forecast, and look at a time series of all these flux variables. So I've selected, so that's what you get. You get a plot. Far be it from me to know if this is scientifically interesting, but it makes a really nice plot. So you can see sort of some annual variations and a bunch of different flux variables. So, that's interesting, but let's go back to the map plot type. Let's go look at this ice concentration. So ice thickness. There's an ice thickness variable. So here we are. We've selected ice thickness. Got an XY plot of that. So one of the things that might be interesting is to see how this ice thickness evolves over time. So one of the ways that we can do that within this interface is to do an animation. So if we get up here to 2021, and if we did that, that would be close to 3,000 frames or something. So let's do one frame every 5 years. So that's going to give us about 20 frames in our 16 frames in our animation. So once every few years, we can check on the evolution of the ice thickness. Now, one of the things to notice about this, as these plots change, you see this top value here of the thickness. It's the same in every plot, so this color scale is the same in every plot. So you're doing a direct comparison. So when LAS does these animations, it goes out, it looks at the block of data, it creates some statistics, gets an idea of what the min and the max are across all the time that's going to be animated, figures out some contour levels that give a nice display across all the time, and then computes the frames after it's done that preliminary work. So that's what you saw, the interaction where it figured out how many frames it was going to compute. It was also figuring out what the contour levels and all those sorts of things that it was going to do. So now we're 15 frames into the process. We're about to turn it loose, and it's going to just start flip booking through each frame, and we can watch the evolution of the ice thickness. The date that we're looking at is shown up here above. Kind of drifts out of December into November. Maybe I'd be a little more careful. I would choose a value that would give me weeks only in December, but you can play around with these interface. You can stop the animation at any moment and step through the frames. If you see something that's particularly interesting, step back, see where it is, Start animating again. Speed it up just a little bit so that it'll flip through there. So that's the animation interface. You can watch evolution of things in time. That's kind of interesting. So this ice thickness is interesting, but it might be also interesting to do some comparisons. So one of the things that you can do is to do some direct comparisons. So here we just have a plot, 2021, 2021 in both frames. So let's just change the axis selection here instead of the variable selection, which is also, you can compare two different variables. But let's go forward in time to 2090, see what the ice thickness looks like. So there, again, we're concerned about comparing apples to apples. In these cases, the plots, the color maps are independent of each other, so that's not an accurate gauge of what we want. So we want to turn on this normalization feature that will allow us to do a direct comparison. So now the color scale on the left is used to make the plot on the right. So there you're seeing a direct comparison. That's interesting. Maybe you want to ask a different kind of question. You want to know what the differences are. So this is particularly interesting if you have a climatological data set that you want to compare. But in this case, in this particular one, all of the difference values are negative. In some I've looked at, you see, the coverage of the ice thickness is mostly negative, but in a few places it's actually thicker. So it's interesting to be able to tease out those subtle differences using those comparison features. All right, so it's a way to look at, we've looked at some time series data, we've looked at some profile data, we looked at some gridded data. I want to do one other data set, and that's a trajectory data set, a sail drone data set. So if we go to the PMEL ERDAP and look at these data sets down here at the bottom, see these West Coast Survey data sets. Now, these are interesting because of the way that they're organized in ERDAP. Up above here, you have these TPOS missions. All of the drones are separated out into their own ERDAP data set, which is interesting, but it's actually not as useful in LAS to organize the data that way. So if you look at this 2018 survey, it had 5 drones. So here's a data set with 5 drones. Let's take that and put that. So that's a single DSG data set, even though it's a bunch of different trajectories from a bunch of different drones. And let's add that to our sail drone container. So now we've got sail drone data. We add that. So now we have the West Coast Survey sail drone data in our LAS. So go back to LAS, reload, start back at the beginning. And now we have the ACLIMB data, engineering data, and now sail drone data. So here's our West Coast Survey. We're going to look at air temperature, and now we're going to see everything. So we're going to see all 5 drones, entire time history of the mission, and it's a lot of data. It's going to take a long time, and people are going to get bored, but sometimes when you're dealing with a lot of data, you got to pay the price of waiting a little bit. But we're gonna work on that. So here we go, 5 trajectories. So that's 5 different boats that sailed this pattern along the coast, 656,000 points. So That's cool, but what if we want to just see the data from one boat? So we can do that by constraining the data set. So here in the metadata, there's one obvious metadata type that's interesting, and that's the ID of the boat. So if I constrain the plot to just looking at boat 1028, I'm going to see where that particular boat went over the entire course of the mission. So that's a single trajectory, 126,000 points. So see where it sailed along the coast just by itself. So that's interesting, but another thing that you might want to do is you want to look at where certain things were true. So we're looking at a plot of air temperature. Maybe we want to know only those spots where air temperature was less than 12. It's always greater than 0, but have to constrain it on both ends. So now, along the course of that survey, there are certain spots where the air temperature was below 12, and those are now represented in this plot. So that's, these are two ways that you can constrain. So we constrained by the boat ID, and then we can constrain by a particular variable. It turns out that in this case we constrained by the variable that we were plotting, but you could constrain by any. You could look for all those. You could look at air temperature every place that sea surface temperature was in a certain range. All right, so that's it. We've looked at 4 different data types: profile type, time series type. We've looked at grids. In terms of grids, we looked at grids that have surface component, but that we also have some variables in the gridded data that have a Z component, so you can slice in Z as well. You can do ZT profiles, that's things like that. And then we also looked at a trajectory data set with a bunch of different parameters, but also a bunch of different boats that are combined into one data set. So those are some of the capabilities of LAS as applied to PMEL data.